Hello, my name is Thomas Rodriguez, and I will be going over Lab 4 for Physics 2212. So to introduce this lab, the purpose is to measure the magnetic field of a bar magnet at different distances. And so the fundamental physics principles, one is the Biot-Savart law, which is utilizing a formula for where the magnetic field is from a constant current. So this is the main Biot-Savart law formula, and this is the one that was given to us for this lab. Then there's also the distance dependence formula, where we are considering the fact that the magnetic field would decrease based off of distance. So it incorporates this formula, the magnetic field of the bar is equal to k r to the power of n, and then this is the natural log equivalent of this formula. For the model, we'll be using a natural log of the magnetic field versus the natural log of R graph. For the system and surroundings, we're going to say that the system is the bar magnet and the surroundings would be any external force affecting the bar magnet. Then for the main results, N would be equal to negative 2.2945, and we found that the magnetic dipole moment would be equal to 5.98 amps times meter squared. For the details of the experiment, we placed a bar magnet along this ruler or this meter stick over here, and then we solved for the magnetic field using this magnometer on the phone, and then we recorded the distances that we used to find the magnetic fields with. And then we also included tapes to align the phone and measure certain instances of where we got our data. And this is our data sheet where we used to record the values from the experiment. So at these certain magnetic fields, we were able to calculate the distances. And then these are for the on-axis points. We also were able to create a line for this natural log of magnetic field versus natural log of R graph. This equation here will come in time, will appear later. And then we also have this off-axis field values where we were able to calculate the perpendicular distance as well as the off-axis magnetic fields. So as for the calculations, we use the equation from the graph as well as the distance dependence formula. We set n as the slope of this equation and then the natural log of k as the y-intercept. So we are able to solve for k, and then we set the Biot-Savart law to the k r to the power of n to solve for the magnetic field. To solve for the magnetic dipole moment, which we get 5.98 amps times meter squared. So as for the coding, we plug in our initial conditions, such as the magnetic moment over here. We create code for the magnetic field of a dipole, and then we set observation locations where two of them are on axis, these two, and then these four would be perpendicular to the axis or off axis. And then we create arrows for all of these values. Then we also plug in the dperp that we got from our calculations over here, and then create an arrow where it's an observation location 45 degrees from the axis. And then we're able to produce this model over here where these two orange arrows are the off-axis values, and these four arrows here are the on-axis values. And then we can compare this with the experimental data, and as you can see, it doesn't really match up, so there's possible that there was discrepancies that occurred in the experiment. So in the conclusion, the assumptions was that the magnetic field would decrease with distance following the distance dependence formula, and that we would calculate using the formula for the magnetic dipole. Some possible errors was that there could have been outside electric forces that could have interfered with the data in the project, such as like phones and computers, and also there could be human errors when measuring the distance using the meter stick. The first what if question, what if we hadn't oriented the experiment to compensate for magnetic north and then laid it with some intermediate angle with respect to Earth's magnetic field? Well, this would have interfered with the data that we got for the magnetic field of the bar magnet, because the Earth's magnetic field would have also played a part in interfering with the data. Then what if you were to stick two identical magnets together and by and run the experiment again? Well, this would have caused the magnetic field to be twice as strong. However, the direction of the magnetic field would go in the same direction. And then the measurements would be basically double what they were originally. And that concludes the experiment. Thank you for listening.